Hello everyone, and welcome to week 3 of the massive open online course 16th semester for the master's degree in digital currencies by the University of Nicosia. My name is Andreas M. Antonopoulos, and I'll be your teacher for today. Now, we have lots of great questions from the forums. Everyone's been studying the material for week 3 and posing their questions in the forums, and we have lots to go for. Hi in the chat, how everyone? Hi everyone, nice to see you all. Nice to see you from all over the world. This is probably the most international course, certainly the most international course I've ever done for the University of Nicosia. We have people from all over the world. Let's see, we're going to start right away with our questions from week 3. The first question comes from Marvin. Marvin asks, why should someone run their own node? A full node, not a mining node, since just the miners that are running a mining node will be considered for the subsidy and the transaction fees. And there are a couple of replies in the forum. Damien offers one reply. It says, I personally run a Bitcoin node because I believe in the technology and the good it will do for society, especially for those in developing nations. Damien expresses one of the reasons why you might want to run a full node. So the 3 reasons that we can think of are the altruistic, the self-interested, and the educational. So let's go through those 3 reasons. Damien expresses the altruistic reason why you might want to run a full node. It's good for the network. It builds decentralization, especially if you run a node locally that you control on your own hardware, let's say at home over a broadband connection. So that's a great reason. You're doing it for the good of the network, for the good of Bitcoin, because you believe in it. That's reason number 1. The self-interested reason would be because you need a full node in order to do what a full node does, which is authoritatively validate transactions and blocks. Now, why would you need to do that? Well, the first reason you might need to do that is so that you can answer a very simple but very important question. Have I been paid yet? Let's say you get paid in Bitcoin. How do you know if you've been paid yet? Well, if you control your own keys, if you control your own wallet, if you're attempting to achieve financial independence, sovereignty over your control over your funds, you don't use an exchange to hold your keys for you, because that's simply a bank. How do you know if you've been paid? Well, one way to find out is to go onto a website that has a block explorer, type in your Bitcoin address, and then find out if that website thinks you have been paid. The problem is that when you do that, you're trusting that website. Worse, you're giving them information about your Bitcoin address, and that information has now been associated with your IP address because you just typed it in over a web browser. So you lost a bit of privacy, and most importantly, you can't trust the answer. If you run your own node, you can ask your own node, has this transaction happened? Has this amount been paid? Is the balance in this address different than what it was before? And your node will provide an authoritative answer without asking anybody else. And that way, you can learn if you've been paid. You can extend this example a bit, more automated functions, like for example, if you're running a software wallet or a mobile wallet or a desktop wallet, if that desktop wallet uses servers by the wallet vendor in order to find out what addresses you control and what your balance is and all of those things, then again, you're leaking a bit of private information to that service provider every time you use them. Many wallets nowadays allow you to configure them to connect to your own node. And when you connect them to your own node, nobody knows which addresses you're using on your wallet. You don't send that information over the internet. And again, you get an authoritative answer. And finally, educational. Running your own node teaches you a lot. It teaches you a lot about Bitcoin. It also teaches you about operating systems and network configuration and all kinds of other little tricky things that are great skills to learn. Now, you can learn as little or as much as you want when running your own node. You can go all the way. and build hardware, operating systems, software, compile everything from source, and run it. That's hard, and it does require quite a bit of technical skill. But nowadays, there are great solutions where you can download essentially a Bitcoin node distribution or installation, where you can install it on a simple computer like a mini PC or a Raspberry Pi and run that. Examples would be Raspberry Blitz, MyNode, Umbrel, and others. And once you do that, it's a lot easier to do, and then you can manage it through some kind of web interface or text interface. Damien asks, if you run Bitcoin Core as your node, can you run another blockchain node on the same computer? Well, yes, you can. You can run as many applications and services as you want on a computer, and a Bitcoin node is just an application. It's more of a server-style application. Of course, it's a peer-to-peer. It's not client or server. But it tends to use a lot of resources. It uses a lot of RAM. It uses the CPU fairly aggressively when it's validating a block, for example. And it uses a lot of disk space. So you would estimate that on average you're going to have about 1 to 1.5 gigs of RAM being used by your Bitcoin node. You're going to have about between 200 and 400 gigabytes of disk space being used by your node. And it's going to be using some bandwidth on your network connection. Now, if all of that's okay, and you have a powerful enough computer, there's no reason why you can't run 5 or 6 other blockchain nodes for different purposes. For example, you could run a Bitcoin node, an Ethereum node, a Litecoin node, whatever, a Monero node. In fact, that's often something that people do when they're installing a home node. There's no point in having 5 different computers if you have one powerful enough to run all of those services. Is there any point in running another Bitcoin node next to your existing Bitcoin nodes? No. There's no point in running 2 Bitcoin nodes in the same location. It doesn't really help you with anything. It's going to double your hardware requirements and your network bandwidth without actually achieving anything that you couldn't achieve with one node. Let me quickly jump in the chat and see how things are going. Very good. Everybody's having fun? Manuel asks, can internet service providers censor communications between the nodes of a blockchain? Some internet service providers block communication ports related to torrent downloads, and even some VPN services enable torrent communication as a bonus. Yes, Manuel, you already have part of the answer there. If a service provider blocks specific ports or specific types of traffic from being used on your own home network that you've paid for, it's fairly easy to bypass those blocks. You can change the port that you use for Bitcoin. It doesn't have to be the same port. You can pick any port out of the 65,000 possible TCP port numbers. At the same time, you can also run Bitcoin over Tor. You can run it over VPNs. You can run it over a VPN inside Tor, inside another VPN, inside Tor again. It's going to be very slow, but you can do that. You can also wrap these VPNs in protocols that the internet service provider has no choice but to allow. So a lot of VPNs look like SSL traffic. And so your ISP can't block secure web traffic because you need that in order to access the web. So you can piggyback your Bitcoin traffic on top of a VPN that looks like HTTPS or secure web SSL traffic. And so there really isn't a way to completely block access to these services unless you are prohibited from using a VPN. In fact, in the countries where these things are prohibited, the risk that you run is not that they're going to block the ports or successfully technologically stop you from running these services. It's simply that they're going to impose some kind of penalty where it's not worth doing. So if it's like, you're not allowed to run a Bitcoin server at your house, and if you do, that's 1 year in prison, well, there's no VPN that can protect you from that. So generally speaking, where we see restrictions on the ability to use these types of protocols and services. Those are restrictions that are imposed through legal means, not technical means. And the reason for that is quite simple. You can't really stop internet communication systems from being used in a generic way where you can do pretty much any type of traffic inside any other type of traffic. It's very, very difficult to prevent someone without the penalty of law from running whatever they want over TCP/IP. That's the whole point. Censorship resistance isn't something invented by Bitcoin, of course, quite the opposite. The internet itself is a great example of a censorship-resistant protocol. It makes it very difficult to censor certain types of applications and traffic. All right, let's move on. The next topic is about changes in the Bitcoin protocol. Arva asks, suppose I have some idea that I think Bitcoin Core developers may consider adding to the Bitcoin protocol. How do I proceed with it? Is it as easy as creating a pull request about the same, and developers and maintainers will review it and respond accordingly? Are all changes considered soft forks? And how is voting done when a major change needs everyone's contribution? Please throw some light on the case with the segregated witness fork. All right, so first of all, Parva, generally speaking, because this is a very conservatively developed system, obviously there's $1 trillion running on it. If you simply show up one day with no prelude and you just make a pull request, and that pull request changes something significant to the Bitcoin protocol, it's unlikely you're going to get much consideration for that. Usually these things are introduced in a more soft and gradual approach. The first thing you would do is try to find out if such a thing has been proposed before, or if alternative ways of doing that thing already exist. You'd be surprised how often people end up reinventing the wheel of things that either already exist or can be done in another way that already exists, or have been proposed before and have not been adopted for good reasons. There was extensive debate. So when you want to make changes to the Bitcoin protocol, the first step is read a lot about everything that's happened before so that you can catch up with the conversation. But after that, generally speaking, what happens is developers will propose things with specific examples of applications where those things might be used in discussions, in conference presentations, in online chat through IRC, and on the Bitcoin developers mailing list. They'll get a conversation going and debate, and very often they'll find out whether this has been proposed before or something like that. So the first step isn't a pull request with a code sample. That takes quite a while to get to. The first step is a conversation. You start a conversation and solicit feedback from people. The second step usually is some kind of Bitcoin improvement proposal. So you write a specification. You specify in more detail, okay, here's the idea in more detail, here's how it would work, here's the structures that would need to change, and here's some example code. Then you would test that code yourself on the Bitcoin testnet or Signet or one of the other test networks without real Bitcoin, where you can make changes and try something out on a small localized network. And then finally, if there is strong support by the rest of the developer community and there are applications that need this, then you go into a conversation of how do we introduce this into Bitcoin Core, what should the code look like, how should it work, and how should it be activated. Activation is a whole other discussion. It usually happens at the end, which is, okay, now that we've agreed that we want to make this change, how do we bring it to the live network in a way that coordinates the activity of multiple actors? There are already a number of activation mechanisms, including various mining voting mechanisms like those used for SegWit. And one of those was recently used for Taproot, which is going to be our next question and topic of discussion. So those are usually soft forks, and they involve voting by miners and some mechanism to decide what happens if the miners don't vote or do vote, and when do you lock it in. The current mechanism for that is called BIP9, and there's a few varieties or variations of BIP9 that are used for activation. So that's the process. It often takes years, especially for a change that affects consensus and requires coordination. Taproot, for example, took just over 3 years. The next question comes from Glenn, and Glenn asks about Taproot, BIP 340, 341, 342. Please discuss the upcoming updates to the Bitcoin protocol. Taproot, as it's commonly known, is a collection of 3 changes to the Bitcoin protocol, which have been described in 3 Bitcoin improvement proposals, BIP 340, 341, and 342. And each one of those is Taproot, Schnorr signatures, and TapScript. Schnorr signatures are a new type of signature mechanism that is different from the elliptic curve digital signature algorithm we use today. TapScript involves some changes to the underlying scripting language, including the introduction of Merkelized syntax trees, which allows us to compress scripts on the blockchain. And then Taproot applies on top of those other 2 changes and allows you to have a signature for an entire set of conditions that looks like a single pair when everyone agrees. These 3 changes were proposed, tested, developed, tested again, changed, and further developed and tested until they were put to a vote through an activation mechanism called speedy trial that was agreed in July, if I remember correctly, of 2021. And that activation, once all the miners had voted and it passed the threshold, will activate in November. So in November, specifically at a specific height in the blockchain, on a specific block number, this feature will be active and will be usable on the main production Bitcoin network. To summarize as much as possible, these 3 changes involve some new signatures that give us better optimizations, that make some very useful script tricks possible, and that optimize the space that we use on the blockchain to store transactions, giving us a bit more capacity, and they greatly optimize privacy for the Bitcoin network too. All right, our next topic is public and private key related stuff. So the first question comes from Hakan. Hakan asks, what is the best way to replace a weak private key, let's say one that was generated by a wallet using a mnemonic phrase, with a private key that is perfectly random? Is it possible to achieve this without creating a new transaction that transfers Bitcoins and pays transaction fees? I'm not exactly sure what you mean by a weak private key that was generated by a wallet using a mnemonic phrase. Mnemonic phrases, if by mnemonic phrase you mean a BIP39 randomly generated 12 to 24 English word mnemonic phrase backup, those are not weak. They're as strong as a perfectly random private key. They are generated perfectly randomly. If by that you mean what we used to call a brain wallet, where you take a common phrase that you created, not randomly, an English phrase like Mary had a little lamb, and you use that as the basis for a private key, that is indeed a very weak private key. It's a terrible idea. Don't use brain wallets. And then you should replace that with a private key that is perfectly random. There is no way to do that other than by creating a new transaction and moving the money to a new address that is secured by a stronger private key. You can't change private keys without changing the address, because the address is derived directly from the private key. The address is an identifier of that private key. And therefore, one private key produces one address. In order to have a different private key, you have a different address. And in order to move money from one address to another address, you have to do a transaction. So there is no way to replace a weak private key without a transaction. The next question is from Eve about private public keys and how they function in a transaction. Eve says, I am not sure I fully understand the order of all of the steps followed in a transaction till it's completed on the part of the private public keys function. Please confirm. Step 1. While a transaction is initiated, we create a message which is signed with the help of a private key. The message consists of the details of the transaction, but no money is transferred yet, correct? Yes, the message is the transaction. You basically create a transaction locally on your computer or your hardware wallet or your wallet, and that contains all of the fields of a transaction. It's a transaction. It's not a transaction that's being recorded yet, but it is a transaction. It's the same structure. And that is signed. The signing function will take the parts of the transaction you're assigning. Let's assume a regular normal signature, which takes everything in the transaction, and then signs it with the private key. Step 3, then we use a public key to pick the Bitcoin address of the receiver? No. The Bitcoin address of the receiver is already in the transaction that you created. So when you first create a transaction, before you sign it, the transaction inside says, take money from here, your addresses, and send it or put it here, these addresses. So the recipient's Bitcoin address is in the transaction already before you signed it. You made that transaction with its outputs sending amounts to specific Bitcoin addresses of the recipient. The signature that you apply to that transaction has your public key as well and goes in the transaction itself. So you take the transaction without signatures, you sign it, and then you put the signature, which contains your public key, in the transaction itself, in the inputs. You're signing each one of the inputs, and you put the signature in the inputs. Think of it this way. You write out a check. In the check, you says who's going to receive the money, how much money they're going to receive, and which account it's going to come from. All of that information is in the check. The only thing that's missing is the signature. You then sign the check, and you put the signature on the check itself, and then you send that check. So that's the same process with a transaction. Then you take that transaction that's been signed and the signature has been put inside that transaction, and you send it to other nodes on the blockchain. They will each validate it. They will validate the signature. They'll validate the transaction details. They'll validate the destination address. They'll validate that you have the money. They'll validate everything about it. And then if they find it valid, they'll propagate it to others. And as they propagate it, eventually it's going to reach a miner. The miner will then take that transaction and put it in a block. When they mine that block is going to be sent back to everyone in the network. And now everyone knows that that transaction happened because it's in a block that's being mined. The receiver then now has a block mine that contains a transaction that says that their Bitcoin address has been paid. They can now reference that transaction in their own transaction. If they want to spend it, they use the transaction where you paid them as the input in a transaction where they're going to pay someone else. So your outputs become their inputs. Their outputs become someone else's inputs. Those inputs become someone else's outputs, etc., etc., etc. So transactions take amounts that have previously been recorded on the Bitcoin blockchain as inputs and create new outputs in the transaction that can then be referenced by another transaction as inputs, creating this chain of transactions. All right. The next question comes from Jake. Public-private keys on exchanges. Jake asks, can you explain the difference between the public and private key as it is related to cold storage versus centralized exchanges? If you keep cryptocurrency offline in, let's say, a ledger Nano, which is a hardware wallet, how do you find your public-private key? Is the private key just embedded in the hardware, or is it actually known by the owner? The private key is generated on the hardware, and it's not generated as a single private key. Rather, it's generated as a sequence of keys in the structure of a tree and all of that is backed up with a mnemonic phrase. So when you first get a ledger Nano, there is no private key in it, but it has a random number generator on the hardware. When you initialize it, it will generate randomness. That randomness will then be backed up as a mnemonic phrase, a series of English words. That's useful for you to back up just in case you lose the ledger Nano or it breaks or whatever, and you want to replace it and get back your money. That mnemonic phrase, those 12 to 24 English words which were generated at random, are the basis for all of the keys that are on that device. Once you have that backup, you can recreate all of the keys that are on that device, or you can recover that backup onto a new device, and it will produce the same private keys. Now, this piece of hardware now has in its memory the mnemonic phrase and the ability to generate all of the keys that are derived from that mnemonic phrase, billions of keys, and it just starts generating one at a time. The first key it generates will also generate a public key and an address, and your hardware wallet can show you that on its screen, and also on your companion software on your desktop or mobile that makes it more usable. And so from there you have an address in the form of a QR code or a Bitcoin address that you copy and paste that you can give to people so that they can pay you. So the private keys stay on the hardware always. The only way to recover them is the backup mnemonic phrase you have. George asks, does a hardware wallet like Trezor T, that's a different type of hardware wallet, randomly create a new private key and public key for each transaction, or does it simply hold one private key and one public key for repeated use? I can see on the online wallet multiple addresses, presumably generated from hashing multiple public keys, which turn arise from different randomly selected private keys. So if multiple private keys are generated, what does the seed phrase connect with? So let me expand a bit on that. This follows on from previous discussion. The seed phrase, the word seed gives you a hint as to how this works. The seed phrase is a backup. It produces the root of all of your keys, and it grows a tree of keys. Plant a seed, get a tree. On that tree, you have a number of keys that are derived from that root. And they're not each randomly generated. Only the seed is randomly generated. The seed is then used to derive all of the other keys. And this is called a hierarchical deterministic wallet. Deterministic because the other keys are not random. They're determined from the seed. So the seed is the root, and from that you grow the tree of keys. So when you see different keys in your wallet, different addresses in your hardware wallet, all of those are a sequence of addresses generated from a sequence of private keys, each of which have been derived in turn from the same seed. So one seed to back them all up, and then billions and billions of private keys generated in sequence, and they're numbered. You have key 0, private key 0, which generates public key 0, which generates address 0, and that's your first address that you use to get paid. And then private key 1, private key 2, private key 3. Each one of those has public key 1, public key 2, public key 3, address 1, address 2, address 3. And it goes on, literally billions. And so you don't have to remember any of that because the seed can reproduce the same sequence of keys anytime when it's recovered onto any device or piece of software that knows how to do the derivation mechanism. That way you don't use the same address or key for every transaction because that's both a privacy and a security risk. But you also don't have to remember or back up thousands of randomly generated private keys because that's an operational nightmare. Instead, you've got this best of both worlds. You have multiple private keys, but because they're all deterministically derived from the same seed, you only need to back up one seed, and that has all of the keys for all of the cryptocurrencies, sub-accounts, and wallets you might want. All right. Afros asks about the signature verification elliptic curve digital signature algorithm that is shown on slide 31, which shows how the verification is done with a formula based on elliptic curve calculations on the elliptic curve. This is advanced mathematics. This is mathematics that involves group theory, and there is no simpler way to explain it than that formula, unfortunately. So in order to understand the mathematics of digital signatures on the elliptic curve and how that works, you need to study group theory, math, and fairly advanced algebra to be able to understand that. And unfortunately, I can't describe it in a simpler way than that equation. The best way to explain it is if you take a message and you calculate these two numbers, the signature values, R and S. One is chosen at random, the other one is produced by the signature algorithm. Then someone else can take those same numbers, plug them in to this equation, and if the result they get is the same as, if the result they get with your public key in there is correct, then they know that that's a valid signature. It's as simple as that. The math is not explainable any better than that. Manuel asks, is there a way to show that an elliptic curve has no vulnerabilities, or does it all depend on cryptanalytic efforts that are put into finding vulnerabilities? There are ways to show that certain cryptographic functions, you can actually produce proofs that certain cryptographic functions cannot be solved. Elliptic curve, discrete logarithm problem, the opposite of multiplication on the elliptic curve, also known as the discrete logarithm problem, is one where we don't know a more efficient solution. Well, we do. We know some more efficient solutions than brute force, but not much more efficient. We don't know good solutions to this problem. And if there are good solutions to this problem, then all of the foundation of cryptography around discrete log, the discrete logarithm problem, is broken. All of it. If you can find a solution to discrete log that is not as computationally complex as we currently have, then you've broken all cryptography that depends on discrete log. Now, a lot of very good mathematicians have tried to solve this problem for many, many years. There's no indication that it is solvable any easier than we have now. Quantum computers, of course, can solve it much faster, and because if you're using a quantum computer, then the discrete logarithm problem is no longer of the same complexity of computation. Let's see. Mark asks, is the ECDSA curve infinitely divisible, or is there no limit to private keys possible through this function? I suppose my question is related to the probability of two private keys being the same. In the description of how ECDSA generates a private key using generator point multiplication, I visualize this as a geometric construction. It is stated that it is a point on the curve. So I imagine this line meeting the curve and the intersection being the key location. Is this correct? Yes. If that is the case, does it also follow that as you zoomed into that point, there are an infinite number of points close to the intersection that can be the location of other private keys? No. And the reason is we're not dealing with an elliptic curve on the real numbers. We're dealing with an elliptic curve that is a discrete point elliptic curve, meaning that this function is defined modulo a very large prime number, and each point on that curve is not a continuous point in the real numbers. It is a discrete integer point. So the coordinates of the curve, if you want, if you take a point, its coordinates x, y, can be described as an integer x and an integer y, where that integer is between 0 and, for convenience sake, let's say 2 to the 256. So it's a 2 to the 256 by 2 to the 256 space with discrete points. And as a result, there are not infinite private keys. However, there are many private keys. Many private keys that generate different public keys on this curve. How many? You can do a close estimate of about 10 to the 77, so 10 with 77 zeros. That's how many private keys you can choose that will fit in the elliptic curve. And when you're talking about numbers that big, approximate is good enough. It's enormous, but it is not infinite. Salim asks about Merkel trees. Can you please provide a clear explanation of the Merkel proof and verification mechanisms? Can I please provide a clear explanation? Not on video, unfortunately. I think probably the best explanation that I have provided is in the book Mastering Bitcoin, which you can find online. And we can provide a link in the notes for the specific description in Mastering Bitcoin that shows how a Merkel tree is constructed. To keep things very, very simple, if you had a Merkel tree that only contained 2 points, so it contained 2 leaves, let's call those A and B. And you say these are the 2 nodes in the bottom of the tree, and then there's a root above. So the way Merkel trees work is you take the hash of A and the hash of B, and then the root node above them is produced as the hash of A plus B. Now, what that means is that I can prove that this item A is in the tree by producing the other item that is in the tree at the same level. It's pair, or pair, if you like. So if I know the hash of A, and I want to prove that the hash of A is in the root, I can just give you hash of B, and then you know that if you add those 2 together, you get the root. You can prove, therefore, that hash of A was included in that root. Now, if you take that tree to multiple levels of depth, at every level, I only need to provide one other hash, the one on the other side of that fork. So let's say that the node I wanted to go down is the one that goes from the root. It's, let's say, left, left, right, left, right. Well, for each of those levels, I just need to provide the other side. So I can prove that that's down there by giving you right, right, left, right, left, the opposite side of each of the 2 hashes. So essentially what I've done is, by giving you, let's say, 8 hashes, I can go 8 layers deep on the tree. That means that I can store 256 items at the bottom of the tree, 2 to the 8th, right? And I can prove to you that any one of those 256 items is in the tree by giving you only 8 hashes, the other side of each fork that goes down the tree from the root all the way to the bottom. And you can prove it. You take the hash that you're trying to prove is there, and the other side of it, you hash them together, and you get a value. And then you take the other side of that fork, hash them together, and you get a value. The other side of that fork, hash it together, get a value. Other side of that fork, hash it together, get a value, get to the root. I've only given you one element at each level of the tree, and I'm able to prove that there are any one of the 256 items in the bottom with just 8 hashes. And this keeps growing at that exponential rate. So I can prove that there are any one of 1,000 items in the tree with just 10 hashes, I can prove, 2,000 items in the tree with just 11 hashes, etc., etc. So you get this incredible efficiency in verification. That's as much as I can really do on video by waving my arms around in the air without a whiteboard. It's much better if you check out that particular chapter in the book. Let me check in the chat and see how we're doing. As a follow-up question, is a Merkel tree an example of a zero-knowledge proof? No, it is not. Joe asks, information such as wallet balances are not held directly, but instead abstracted from lower-level data by wallets or block explorers. As I understand it, the purpose of such redaction and abstraction is to reduce the amount of data that needs to be stored on a blockchain. What is the optimal level of reduction? Can Bitcoin code be further reduced? Does this reduction abstraction process have drawbacks? The process actually, I don't think the process is to reduce the amount of data that needs to be stored on a blockchain. In fact, the opposite, because if your wallet needs to reconstruct the current balance of your wallet based on counting all of the UTXO, all of the unspent transaction outputs that correspond to the addresses that belong to your wallet, that means there's actually more information on the blockchain than your wallet needs in order to find the balance. And we can see this very clearly because Ethereum does it the other way. Ethereum does it in exactly the opposite way, and many other blockchains use a different mechanism. So Bitcoin and Litecoin and Liquid and a whole bunch of blockchains use a UTXO model, unspent transaction outputs, where basically transactions are a chain of signatures that construct essentially a tree in the blockchain. And if you want to calculate your balance, you have to count all of the leaves on the tree that are corresponding to your address. That's a lot of information, right? The other blockchains that do this use an account-based mechanism where what they do is they simply keep track of the balance and changes. So it's like track changes. They track the change, but then they only keep the result rather than recalculating it every time you want to find a balance. That's a more efficient way of storing. However, it means that you can't actually prove the consistency of the latest information without collecting all of it from the beginning and running the changes backwards. So what that means is, let's say you have an account-based system and it says your current balance is 10 Ether. How do we know it's 10 Ether? Well, it's because it was +1, -2, +3, +1, -7, +6, -1, +1. Well, in order to get to 10, you have to go back to the beginning and do all of the pluses or minuses and see if it adds up to the same amount. With Bitcoin, you can actually prove that as long as those UTXOs haven't been spent, that is the current balance, without looking at all the transactions that may have happened in the blockchain. So in a way, the wallet balance abstraction isn't a compression mechanism. It's an auditing mechanism. It's in order to be able to audit the consistency of the data storage. And there's pros and cons. And other blockchains, as I just mentioned, have made different decisions on how to balance those pros and cons. Similar question. Mahmoud asks, while the wallet has only the private and public key stored in it, what is the mechanism to calculate the balance for each wallet and for each coin? Is there such a balance field after or in the blocks to avoid unnecessary traffic on the network? No, there isn't. There is in Ethereum. You can calculate the balance by taking a snapshot of the most recent state. It's a bit more efficient, but no, there isn't. And this is why, going back to some of the earlier questions, why you would want to run your own node so that you can authoritatively validate the balance of your wallet. There is no balance field. You basically have to go and look at any transactions that create outputs with the script of your Bitcoin address in them and add up all of those that haven't been spent, and that's your balance. So your wallet may have multiple addresses, multiple private keys, and then its balance as a wallet is the sum of all of the unspent outputs for all of the addresses for all of the keys that it has. And in order to figure that out, it either needs to send that information to a third party, like someone running an Electrum server or the servers of Trezor or Ledger or some other company that is running services for wallets, and say, here's a bunch of addresses, can you tell me what all of the transaction outputs that belong to them are? And you'll get that information back. But as you can see there, you've leaked some information to the internet and you're creating traffic. And that's why you might want to run your own node, because if you ask your own node about the balances of those transactions, it calculates that information based on a database, the blockchain, that it has stored locally, and it doesn't need to ask anybody else. You not only get the correct answer authoritatively based on the consensus rules that your node is validating, but you also don't send information about what addresses you're interested in to third parties. There are other nuances. There are protocols that make it easier to reduce the amounts of privacy damage you do when you ask other servers, such as the Neutrino protocol, but that's beyond the point that you're asking, so we'll leave that for another time. Transactions between separate wallets, same owner. Javier says, let's assume an owner of several separate wallets holds them under the same or related exchanges, Coinbase, Coinbase Pro, or Coinbase Wallet, and that they order a Bitcoin transaction among some of those wallets. The transaction will need to be published in the Bitcoin network in order to be validated because those wallets have different public keys. Now, the question, if the exchange offers certain related transaction for free, does that mean they pay the fee themselves? No, that's not how it works. When you have money on an exchange, it's not stored in your private key. It's pooled, meaning that they have private keys that belong to the exchange, and all of the customer money is in those private keys. Most of it's in cold storage, so it's not easily accessible. But when you ask to transfer from one wallet that's on Coinbase, say, to another wallet that's on Coinbase, there is no Bitcoin transaction. They update their internal database to say, you know, Joe had 3 coins, now Joe has 5 coins. So that they know how much of the money that's in the big bucket of money that they control supposedly belongs to you, so that when you ask for it, they can give it back to you. You don't control any of the private keys, and they don't have private keys specifically for you. They don't have public keys specifically for you, and they don't move money between addresses that they control on the blockchain. Instead, they simply keep their internal accounting database of how much money you own. So therefore, when you're moving money from your wallet to your wallet, or even from your wallet to your friend's wallet, and they're both on Coinbase, there is no Bitcoin transaction that happens. That's an internal database transaction that happens within their own private databases. Now, it's sometimes confusing because when you ask them to deposit money, they'll give you an address and they'll say, here's an address, put money in this, and then it's your money. That address does not correspond to a key that is yours, and they won't keep the money in that address. So those are called deposit addresses. And what they do is they'll generate a unique deposit address for every customer who wants to do a deposit, so that they can identify who that money belongs to when it comes in. But they're not going to leave it in that address. In fact, what almost all exchanges do is they'll have all of these deposit addresses where you can deposit money, and as soon as the money comes in, they sweep it. They make a big transaction that says, take all of the money from all of these addresses, put a note in our database that these people got paid, and then dump all of this money into the bucket, the hot wallet. And maybe they'll use the money you just sent in to do a withdrawal for someone else. It's not your money. It's not your address. They only used it to identify the payment when it came in, and then it gets mixed together in the big bucket with all of the other money. In fact, you can watch this happen. Next time you do a deposit to an exchange, go see what happens within 24 hours to that money. You'll send it to a specific address, and then go on a block explorer or use your own nodes to explore and find out whether that money is moved. And you will notice within 24 hours, maybe a bit longer sometimes, that money will move. It will move in a massive transaction that involves hundreds of other addresses, and it will go into a big bucket of money, into these addresses that have enormous amounts of Bitcoin, many of which are cold storage, so they'll get swept into cold storage, or they'll stay in a hot wallet, depending on the activity that's happening on the exchange. Scripts. Javier asks, Bitcoin scripts mentioned in the materials resemble smart contracts in Ethereum, but more basic. That's a very valid observation. What level of transaction flexibility or ability to perform beyond a mere transfer of funds do these scripts provide? You'd be amazed. The follow-up question, of course, is could Bitcoin improvement proposals or other kinds of future developments in Bitcoin software make it supersede Ethereum over time? This is where things get interesting. Bitcoin script does offer some surprisingly flexible capabilities that you can do interesting things with, including things like making payment channels for the Lightning Network, creating various forms of simple smart contracts. Absolutely, it is a scripting language and you can program it. However, it is not a Turing-complete scripting language, which means it doesn't have loops and it is limited in the amount of computation it can do, and that's done on purpose. The reason it's done that way is because a non-Turing-complete or a Turing-incomplete language is simpler. It has predictable runtime, meaning that when you try to verify a script, it can't run forever. It will run for a specific amount of time based on the length of the script, and that's it. It can't go into a loop where it just keeps running. Ethereum, on the other hand, is a Turing-complete scripting language where the Ethereum virtual machine can go into loops and those loops can run forever. Ethereum solves that, or gets around that, by using a metering system, gas, in order to prevent it from running forever. And we'll talk about Ethereum in the future weeks and subsequent weeks of this course. So this is a matter of trade-offs. Very simple scripting language that allows surprisingly complex smart contracts, but at the same time not an infinite complexity of smart contracts. And this keeps the system secure, predictable, with predictable runtime, and it prevents certain types of security vulnerabilities. That wasn't good enough to build something like Ethereum, so Ethereum has Turing-complete scripting language, and with that comes a whole lot of baggage, because in a Turing-complete language with infinite complexity and expressiveness, you can do whatever you want, including make some very big security vulnerabilities emerge that are not obvious, and it's much harder to audit that code and know exactly what it's going to do in all circumstances. In fact, you can prove mathematically, this is the Turing theorem, that you cannot know exactly what the code will do under all circumstances. This is known as the Turing completeness problem. It's this thing we study in first year, first class of computer science. So it's an interesting trade-off. Can Bitcoin supersede Ethereum by becoming more complex? Only if it becomes more like Ethereum, and then it stops being more like Bitcoin. So Bitcoin doesn't want complex smart contracts, because Bitcoin was designed not to have complex smart contracts on purpose. And the purpose is to have super secure, very robust, predictable execution, which makes Bitcoin suitable for being very sound money and very secure money. Ethereum chose a different path, more complexity, more expressiveness, at the cost of less security, or much more difficult to achieve the same levels of security, if not impossible. So Bitcoin doesn't want to be like Ethereum. And the reason it doesn't want to be like Ethereum is because in order to do so, it has to give up what makes it special. And if you want to understand this, this basic trade-off, I've done a video that you can find on YouTube called The Lion and the Shark that expresses how you can have two very well developed systems that are each kind of the apex predator of their specific domain, but it doesn't make sense for them to try to copy each other. The lion doesn't need to learn how to breathe underwater, and the shark doesn't need to learn how to walk. Those are not useful adaptations. In fact, they make each of those things less adapted to the purpose for which they have adapted. All right. Charlotte asks, with China's recent crackdown on mining, where do you expect mining capacity to migrate? This is a fantastic question. In fact, I was reading today that now it is estimated that 35% of mining capacity is now located in the United States. And that makes a lot of sense. The United States has robust electricity infrastructure. It's not the cheapest in the world, but it has the kind of business environment where you can set things up with a bit more certainty and a bit less regulatory risk. The biggest risk you have in mining isn't the cost and availability of electricity, as we've seen recently, it's the regulatory environment. If you can get banned in a weekend without any review, appeal, legal process, just like that, that's an enormous risk. That means your business can simply be wiped out. It is extremely unlikely that that would happen in a business environment like the US. So as a result, that makes it appealing. Not perhaps as appealing as other places, and mining is now getting much more international. We've seen a lot of it move to North America in general, so not just the United States, but also Canada. A lot of hydro is a very suitable source of energy for Bitcoin mining. Other people have said places like Kazakhstan. Who knows? We'll see. This is an evolving industry. What's surprising to me is how resilient this industry and the systems that it secures, Bitcoin, have been to what would otherwise be, and what many people thought were going to be, fatal attacks against Bitcoin. So when we started talking about Bitcoin dominance in China of mining, mining dominance of China, this was the doomsday scenario: was China tries to take over mining and crack the network, or China bans mining. Turns out that's a survivable event. We now know that China banning mining and then banning crypto again is a survivable event. It only proves that Bitcoin is more resilient than we thought, and it's now going to become even more resilient as it decentralizes its mining infrastructure. This is not over. This is going to be a long story. Mahmoud asks, which came first, the seed phrase or the private key? That's a great question. The seed phrase comes first. So randomness is generated from which 12 to 24 English words are produced, and those 12 to 24 English words are put into a hashing function through multiple rounds to produce a master private key, and that master private key is used to derive a series of Bitcoin private keys or Ethereum private keys or other private keys for various cryptocurrencies in the structure of a tree. So randomness, seed, root, tree, lots of little keys. The seed comes first. Now, you could just randomly produce one key. The problem is then you have to back that up. And you either have to keep reusing that key or you have to back up multiple keys. And that's the place we were in 2012, 2013, before the introduction of hierarchical deterministic wallets and mnemonic phrases or seed phrases. Now we have this technology which is much better. You have one single backup your seed phrase, and from that you can always regrow the tree of keys. The seed comes before the tree of keys. And that's all the questions we have time for today. What a great session. Really, really good questions. Lots of topics covered today. I hope you enjoy that. I hope you enjoyed today's presentation. We'll see you next week. Study the topics, look at the slides, and don't forget to have conversations in the forum. You will learn a lot, not just by reading and asking questions, but also by trying to answer other people's questions or engaging in the conversation. That's probably one of the more valuable aspects of this course, is the ability to have these conversations in the forum with your fellow students and learn from each other. In fact, I know many students take this more than once, and as they get more and more confident, contribute more and more into the forums. So we can all learn and teach each other. I will see you next week. This has been week 3 of the 16th semester of the Massive Open Online course for the Master's Degree in Digital Currencies by the University of Nicosia. My name is Andreas M. Antonopoulos. I was your teacher for this session, and I'll see you next week. Thanks so much.